This is Module 4, Part 2. There we go. Let's see, do we remember anything from last time? I don't know where we've been. Let's quick go over where we've been, and then we will continue in terms of where we're going. So we talked about pure substances and mixtures. That's on page 1 of your notes. You'll need to differentiate between the two of those to understand what they are in very simple terms. I asked you about that, okay, on the test. Homogeneous mixture, heterogeneous mixture. You'll need to know those in terms of examples, how to identify examples in terms of something that is the same throughout the compound versus it being different throughout the compound. And so I'll give you some examples on the test. So you'll have to think about that. You know, the classic example, like we said, was Italian dressing in terms of a heterogeneous mixture. So you'll have to think about those things. The two types of change are chemical and physical change. That's what you'll be asked about that too, just in terms of being able to identify a couple of different aspects of that. So physical change would be taking the piece of wood and using an axe and cutting it in two. You have separated the two, and it would be difficult to put them back together, but you haven't done anything in terms of the composition of the wood. But if you were to apply an energy source to that wood and set it on fire, you would then commit chemical change. You have changed what it was into some other things. So those are differences there as well. And the key to them is chemical change can't be easily reversed. It isn't as easy to put the water and the carbon dioxide and the other gases plus the ash back into a piece of wood. Phase change, just in terms of identifying the different phases and understanding them and how they get there in terms of melting, freezing, and boiling. Condensing, of course, is going out of the gas into the liquid, and freezing from the liquid to the solid. Phases of matter are those three. And then we also identified the unique property of water, and that is that the density of solid water is actually less than the density of liquid water, which is an amazing reality, and as we said, unique and absolutely critical, necessary in order for life as we know it to exist. That's the only thing that we know of, at least what we're going to discuss in this class, that does that. So everything else, obviously the solid would have a greater density than the liquid, and the liquid a greater density than the gas. So if you're asked about any other compound, you're going to tell me that, oh yeah, the solid has a greater density than the liquid or the gas. Melting point liquid in terms of the temperature at which a substance changes from a solid to a liquid. These things are fairly intuitive, so I don't think we need to go into those things. We talked about temperature being the function of something moving, and of course the example is the mercury or whatever compound might be in the little glass tube of a thermometer. So something has to move in order for temperature to be measured. All right, so is there any questions then about what we introduced the last time? And as I suggested to you, all those are concepts, and they're not tough concepts. You just need to be familiar with them and familiar with where they are in your notes, and to be able to think them through when I ask you, as I said, you know, perhaps some aspects of homogeneous versus heterogeneous mixture. What you know, thinking that through. Is there questions about what we did way long time ago at the beginning of October? How can it be the 15th? I don't know, but it is. Questions? Okie dokie. All right, well, if you would, we're on page 2 of your notes. We are at the bottom of page 2, near the bottom of page 2, and you see chemical reactions and chemical equations. So here comes the repetition, the repetition, the repetition, the repetition. The tests are not cumulative, but the material is. And what you're going to be introduced to today, you will be doing for the rest of the course. So in terms of learning it, how do you learn it? You practice it in terms of doing the homework. And this is not hard stuff. Don't turn it into something that, you know, it's not. It's what we're going to do is balance chemical equations today. And all we're going to do is count up the number of atoms of the different stuff, the different ingredients in the chemical equations, the reactants and the products, and make sure they're equal. And it involves a little bit of math, but nothing that you can't do. So in any respect, so let's introduce the term. A chemical reaction is a process by which one or more substances change into one or more different substances. So again, a straightforward definition of what a chemical reaction is. It's just the process of a couple of things changing their chemical composition, and you track that by virtue of a digital chemical reaction that we're gonna look at. But before we do that, I have some other things to introduce to you. Things called homonuclear diatomics. All right. So for this, I'd like for you to kind of keep handy your handy dandy periodic table to track these things. And at the bottom of 115 in the bolded section, that's what I have for you in your notes at the bottom of page 2. Homonuclear diatomics are something else you will be required to sort of keep up with for the rest of the course. So does that mean memorizing them? Not necessarily. It just means becoming familiar with the fact that these gases, these nonmetals, exist for the most part, not for the most part, they exist in nature as doubles. All right, they're twins. They always walk around together. All right. So look at at your notes at the bottom of page 2. Homonuclear diatomic elements are composed of individual molecules, not individual atoms. And so what we mean by that is that nitrogen doesn't exist, and so in the form of a chemical equation, it does not exist as an individual. It always exists as two, and we will, in the modules to come, we'll watch how that works in terms of their elemental makeup. We'll see how it works and why that it has to be that way in terms of these elements. But for now, all you are required to know is the fact that they always exist in pairs, all right? So it's not that you will ever have a single oxygen atom floating around in the air if that's all it is, if it's just oxygen. It will always be O2. You'll never have a chlorine atom just existing as Cl. It will always be Cl2. Now, take a look at your periodic table and notice the positioning of these things on the periodic table. So there's nitrogen, number 7, oxygen, number 8, fluorine, number 9, just below it, number 17, chlorine, bromine, number 35, iodine, number 53, and astatine, number 85, and then the one exception to the little location there, hydrogen sitting by itself up at the top. So you know, for the sake of remembering them, you have them there in your notes. If you're keeping track of your periodic table, maybe you want to circle them or something, you know, highlight them in some way so that you can remember or identify them as being homonuclear diatomics. So, and as a matter of fact, in Module 5, we're gonna begin to discuss the types of chemical reactions. So, if you do a formation reaction and you have hydrogen plus oxygen, and you want to make water, all right. First of all, the first thing that you have just learned is that can't be any kind of correct chemical equation, all right? That's impossible, because you can't have just a single hydrogen atom, sort of. There's exceptions to everything, so I don't blow your mind later, but he said, it's on tape, I've got him on camera to say. We'll see some sort of exceptions to these things, but for the most part, you just can't have a hydrogen sitting there and an oxygen. It's got to be H2 and O2, all right, to produce water. But we're going to get right into it, so let me just introduce it right now. There's something else that you will notice in terms of numbers. So we have two hydrogens, and lo and behold, they show up on that side. There's two hydrogens there. But we also have two oxygens, and we're missing one. So what's a person to do? How in the world could we possibly make that work? In other words, for all of the atoms that we had in the reactant side to show up on the product side, to account for them all. We haven't lost them. Remember, we can't destroy any matter. In the process of the formation reaction, we haven't destroyed that oxygen atom. But what's happened? What's happened? Well, in terms of it, all we have to do is adjust what we understand to be our numbers. So instead of one homonuclear diatomic molecule of oxygen reacting with one molecule of homonuclear diatomic hydrogen, instead, in terms of our desire to form water, we have to use two molecules of hydrogen, the homonuclear diatomic hydrogen, and we end up producing two molecules of water. So here's 2 4 hydrogen atoms. We've got 2 4 on this side. We've got 2 oxygen. 2 times 0 is 2 oxygen on that side. So what you have just seen is where we're headed next. We are balancing chemical equations. We're going to talk about chemical equations, and then we're going to go ahead and go there. We're going to balance them. And you're going to be balancing chemical equations for the rest of the course. So I'm just telling you, in terms of this particular material, make sure you understand it. Practice it. Again, there's nothing hard. They get a little complicated in the sense that, you know, the chemical equations of some of these reactants and then the products will be perhaps a little complex. And it might require you to think a little bit more in terms of doing the math, so to speak. But they're not hard. You're sort of following the bouncing ball from one side to the next. All right. So well, that's the introduction. But let's go ahead and do our notes and keep going. So a chemical equation is, I'm at the bottom of page 2 of your notes, a written representation of the chemical equation. So, you know, this is happening, all right, if you had hydrogen and water. As a matter of fact, you do have that in our atmosphere, and it does form water in terms of the chemical reaction. So all we're doing is representing that digitally on paper. So the reactants are the stuff found to the left the left of the yield sign or arrow. All right, so anything to the left of that is simply called reactants. All right? Haha, we've reached page 3 of our notes. How about that? The products are anything to the right of, all right? There you go. Spelling. So anything to the right of the arrow or the yield sign is what you're producing. So you're reacting some stuff, that's on the left side. You're producing some stuff, that's the products, that's on the right side of the arrow. Let me stop there and see if there's any questions. It's not hard stuff, is it? Anything there? Have you seen this before? Anybody seen these things? All right, well, good. That was a nod. How about that? Good, good. All right, so balanced chemical equation. I just introduced it a moment ago. Let's see. We'll look at a couple of the examples in the textbook and go from there. Turn over to page 117. Burning carbon at an atomic level. So, in terms of it, you see the production there in little pretty pictures. So a balanced chemical equation, I'm now reading from your notes, contains the same number of each type of atom in both the reactants and in the products. That's a balanced chemical equation. Yes, sir? What's that? Of course, of course. So again, all you're doing is counting up on the left side the number of each individual atom, either by itself in terms of reacting elements together, or in a compound, elements combined, and making sure that what you have on the product side, you have the exact same number of elements, all right, of each one. And again, they'll be rearranged into different formulas. Sometimes you end up with the same product as you had reactant, but again, the idea is to simply count the number on the left side, on the reactant side, and make sure it's the same number on the product side. And then we're going to discuss, how you go about that. And there's some important aspects to that. Really, it's just one thing that's very important. So a chemical reaction must start with its reactants and end with its products and have no atoms left over. Another way to state what we're talking about this morning. The subscript numbers, for example, if we have homonuclear diatomics, remember, the subscripts are these, all right, the 2 in this case. The subscripts tell you how many atoms of a given element make up the molecule's chemical formula, all right? When you are balancing chemical equations, you can never change those numbers, all right? So if you have a 2 or a 3 or a 4 in a subscript, you can't touch that in terms of manipulating the numbers to make stuff balance, all right? The big numbers to the left of the chemical formula, for example, 2 sodium chloride, or the example we've given here, 2 H2O, 2 water. So this number, all right, that tells you how many molecules they are. We're going to introduce a term at the very end of today, which I'm probably not going to hold you responsible for, because we're going to begin that in short order, and I might add, sadly. It's probably the most difficult part of the course, stoichiometry, but it just is what it is, and it's really not difficult. It's just a matter of following steps. And it's the steps that confuse folks, and we'll work through it. And again, some of you have called me, have emailed me, and asked questions, and I'm thrilled to take them. All right, so we've got to do what we got to do. So, I'm going to repeat it. The subscript numbers tell you how many atoms of a given element make up the molecule's chemical formula. You can't touch them. They are what they are. They always remain the same in a chemical equation. The big numbers to the left of the chemical formula tell you how many molecules there are, and those will be the numbers we will manipulate in order to make sure that we have balanced chemical equations. So again, this number tells you how many molecules of water that we have. That number right there is the same thing. It tells you how many molecules of hydrogen. In that instance, hydrogen diatomics that you have. You have two homonuclear diatomics of hydrogen, and you end up with 2 molecules of water in the process of that chemical equation. So, the last 3 points are simple statements on how to balance. Keep track of all the atoms in the equation. It's, you know, straightforward. Count the number of atoms of reactants. They must be equal to the number of products. And they'll give you an example. It's kind of wooden in the sense of following steps and writing things down to keep track of them. When you have a little bit of practice at this stuff, you'll be able to eyeball it, I would imagine, and say, well, there's that many there, and what do I need to do to make that equal that on that side, and vice versa. So you count the number of atoms of the reactants. They must equal the number in the products. To balance an unbalanced equation, the numbers that appear to the left of each molecule can be altered, as long as they're not made negative. You can't make any negatives, and you can't make any fractions either. We discussed that. You can't make a half a H2. The subscript numbers, I have it again in italics, cannot be altered. All right? Every year I've got somebody that forgets that, maybe somebody's, and they end up, you know, altering the subscripts, and that's just wrong, you know? And so let's just look at this. We're also looking at, me and my math. All right, so what is it? The least common multiple, isn't that it? We want the smallest stoichiometric coefficient, or the number on the outside of the molecule. We want the smallest one we can get, all right? So, you know, you might be able to make it work with, well, in this instance, here you go. So we've got 2 H2O. Well, you could make this work the same way. 4 H2, 2 O2 would yield 4, let's see, yeah, H2O, isn't that right? Didn't I do the math right? You got 8 hydrogens there, 8 hydrogens there. Let's see, 4 hydrogens there and 4 hydrogens there. So what we did was alter the stoichiometric coefficients, or as we're describing them today, the number of molecules, and the math works, right? It's all the same, but the problem is, in terms of solving these things, we don't want the larger number, all right? We want the least common multiple. Somebody help the boy, isn't that what it is? Isn't that what it's called? Don't ask me to teach you math, all right? We want the smallest one possible, okay? Now, you know, if you give me 4, you know, H2 and 2 O2 yielding 4 H2O, the first time I probably won't mark it off. You know, I'll refer to it because your math is right, and that is what it would ultimately produce. But in terms of balancing these chemical equations, we want the smallest number, all right? Let me stop there before we begin some examples. Maybe I ought to do them. Questions? Anybody scared of this stuff? Oh, I've always wanted to balance chemical equations, and we've arrived at it. Isn't that the case? Actually, this isn't bad. I kind of like this stuff in a weird, sort of twisted way. So on page 117, There you have it sort of in drawing form. So in terms of the chemical reaction, you've got a carbon atom, and the carbon atom is not a homonuclear diatomic, right? You can look at your list, or since you have highlighted them on your periodic table, you see, that's not a homonuclear diatomic. So one carbon atom plus an oxygen molecule in a formation reaction will produce a carbon dioxide molecule, all right? So that's pretty straightforward. And incidentally, there's another aspect to this. So when you do have you notice I didn't put a 1 on the outside out here. So if you only have one molecule of something, in this instance carbon, you wouldn't put a 1 in front of it. It's just a given, the fact that it's just a single carbon. Notice the chemical formula there in the middle of page 117. So carbon plus O2 yields CO2. All right, no 1s in front of any of that stuff, because again, you don't write 1s. Turn over to page 118 and 119. So the combustion of methane. We're going to talk about combustion reactions next time. As a matter of fact, we're going to introduce them anyway. So you start with methane. There it is, CH4, and you're gonna add a little energy and combust that. You're going to burn it in the presence of oxygen. Of course, combustion can't take place without oxygen. And oxygen always exists as a homonuclear diatomic, O2. So the oxygen molecule splits apart, so does the methane, and you end up with CO2 and 4 hydrogens left over. Well, no, that's actually not the way it works in terms of forming these products. Look at the combustion of methane, the correct approach. So in terms of it, once again, the reasoning there is, of course, that the hydrogens, in terms of their and again, you'll learn this when you learn to identify the combustion reactions, but anytime you combust a carbon-based compound, you will always produce, that is, if it's complete combustion, if you burn it all, if you got lots of oxygen, you'll always produce carbon dioxide and water, and that's what they're showing you here in terms of the next step. But the point was, you're not going to have just 4 hydrogens left over in that combustion reaction. What you want to do is add more oxygen to your reaction, and you're going to end up producing carbon dioxide and water. They introduced that by virtue of giving you the chemical equation at the top. They showed you that methane and oxygen produce carbon dioxide and water, and of course, just by doing single oxygen molecule and a single methane molecule, you can't get there. You have to add, in terms of this thing, you have to add some extra oxygen to the mix and ultimately produce, look at the tracking of this thing on page 119. So they show you the methane, and then they show you the 2 separate oxygen atoms, the homonuclear diatomics, and then they show that produces the single carbon dioxide molecule, and then 2 different hydrogen molecules. And that's an acceptable way to show that, but it's also lengthy, and it's ultimately, when we're talking about balancing chemical equations, it's not the right way. So instead, you're going to put a 2 there in front of the oxygen. I'm looking at the bottom of the page, figure 4.5, bottom of page 119. You have the methane. You're going to put a 2 in front of the oxygen to indicate the number of oxygen molecules. Again, that term, I'm giving you the term even though in this module you're not going to be held responsible for it. It's called a stoichiometric coefficient, but that coefficient in front of the oxygen molecule is 2 because you have 2 of them, and it's going to produce 2 water molecules. So the 2 goes in front of the water as well. And so you end up with a balanced chemical equation. Let's keep going on this. Let's look at something else. let's look at the example and see how they do it. Again, I suggested to you that their examples are rather wooden, and what I mean by that is, you know, they write down specific steps. Look at in terms of the reactant side, they write down and follow how much of each thing, and then they do the same thing on the product side. And again, to begin this process of learning, of balancing chemical equations, not a bad idea. I mean, that way you keep track of stuff, right? So you write down what you got, and then you start doing your calculation to put stuff together. So determine whether or not the following equation is balanced. You've got 2 HCl, 2 hydrochloric acid, and some calcium bromine, and you produce then 2 HBr and 2 calcium chloride. So is that thing balanced? And what they do is start counting. So on the reactant side, you've got 2 hydrogens, you've got 2 chlorines, you've got a calcium, and you've got 2 bromines in terms of this. And they take the reactants and the products over to the next page. So perhaps that's a little confusing, but anyway. So they listed 2 hydrogens, 2 chlorines, and on the next page they've got the 1 calcium and the 2 bromines listed as reactants. Follow the same thing on the product side. They counted, and they've got 2 hydrogens, they've got 4 chlorines. Aha! Houston, we got a problem. And then in terms of the calciums, they got 2 of those too, and then they've also got 2 bromines. Now the bromines add up just fine. So how are we going to balance this chemical equation? And they say this: if an equation has even one type of atom that's not balanced, the whole thing is not balanced, therefore the equation is not balanced. So what you're going to do then is start adding some numbers to the stoichiometric coefficients, or the numbers to the left, the numbers of molecules, and see if you can get them to balance. You look at the thing and you say, well, what can I do to those carbons and those oxygens to get them to add up in terms of this thing? And so in terms of balancing this one, they don't do it for you in this example. They just ask if it is balanced or not. But the point is, you start adding up on each side and sort of changing things a little bit, and getting to the point where you have equal numbers on both sides. So let's look at the example. I want to take you through the example so you see something. You'll have it right there in front of you. You can use it as an example to kind of follow through in terms of their recommendations. This is very simple. It's the equation is nitrogen plus hydrogen yields ammonia gas. And you see immediately that you're not balanced, because you've only got 1 nitrogen on the product side, and you got 3 hydrogens on the product side as well, and only 2 on the reactant side. So I'm just going to read what they say, because it's right in front of you and you can go back to it. How can we balance it? We must change the numbers in the equation so that each individual type balances. Remember, you can't touch the numbers in the subscripts. We can only change the numbers to the left of the molecules. Let's concentrate on the nitrogens first. Now, why do they want to concentrate on the nitrogens? There's no good reason. You just pick one. But in this instance, the nitrogen happens to be to the left of the side, and in terms of the chemical formula of the ammonia, it comes first. So maybe that would be something to work on. So there's 2 nitrogens on the reactant side, but only 1 on the product side. To fix this, we gotta, let's see if we can just double the number of nitrogens on the product side and see how we can work that out. So they put a 2 in front of the ammonia on the product side. So now your nitrogens are balanced, right? We're good to go. But the 2 turns the hydrogen into 6 on the product side. You got 3 hydrogens times the stoichiometric coefficient. 2 times 3 is 6. That's not 2 plus 3 equals 5. It's 2 molecules of this NH3. So you have a total number of 6 hydrogens now because you've added a 2 to the ammonia on the product side, all right? All right, everybody with me on that? We following that? You following the bouncing balls? All right, there we go. So if you got, our nitrogens are fixed. We did that when we put the 2 there. So now we got 6. So what can we do to the hydrogen on the reactant side to fix that? And it's pretty straightforward and apparent, right? Just put a 3 in front of the homonuclear diatomic in terms of the hydrogen, and voila, you got a balanced chemical equation. You got a recipe that works, and that's what they show you there. So once you decide to do something to try to fix the equation, what you do is just track it through what it does to the other atoms in the chemical formulas, and see if you can do something fairly simple to fix that on the opposite side of the chemical equation. And that's what they do, and then they show you in terms of excuse me, the total numbers there at the bottom. Let's go through one more just to do it before we get out of here. Write a balanced chemical equation. I'm on page 124. Write a balanced chemical equation for the following reaction. So propane reacts with oxygen to make carbon dioxide and water. So what have we just done there? We've managed to blow your mind because they didn't give you the chemical formula, all right? I might do that on the test, but I won't do anything that's dramatic, anything difficult. Some stuff that you will have worked with, easy stuff, like they do here in terms of carbon dioxide and water. Those are fairly simple compounds that you should be able to recognize, and if not, what do? You Google them, or you look in your textbook to try to find the chemical formula. That's what you do, all right? So they didn't give you the chemical formula, but you just produced it. So you've got the propane, they gave you the chemical formula for it. You're reacting it with oxygen, so it's not O, all right? It's got to be O2. If anytime you're reacting one of the homonuclear diatomics, it's got to be a subscript 2. You're going to produce carbon dioxide, the chemical formula of that CO2, and water, H2O. So there's our chemical formula. There it sits. Well, immediately, and they count up the number of atoms in terms of trying to see if they work, but let's see. We got 3 carbons on one side. We only have 1 on the other, so we immediately know it ain't balanced. We've got 8 hydrogens, and that's not even close. And then we've got 2 oxygen, and we've got 3 on the product side. So none of those are balanced. So in terms of this, you can pick any of them, but since carbon is to the left of everything, let's see if we can make that work. Well, and that's basically what they do too. They put the 3 in front of the CO2, and so now the carbons add up. We're fixed with regards to the carbons. Well, we've got a problem though with the oxygens and the hydrogens. So in terms of making the hydrogens and the oxygens work, we're just going to have to take a stab at other numbers to see if when you multiply them, you can do something to make them all add up. And so what this guy does is he goes ahead and solves to try to fix the hydrogens. That's the next thing in line in terms of the propane chemical formula. So how would you fix the hydrogens? Well, you put a 4 in front of the water, and now we've got 8 water, and that adds up with the propane molecule, and the carbons are adding up because you put a 3 in front of the CO2, but now we have to try to fix the oxygen. So because we put a 4 in front of the H2O, we now have 4 oxygens, and because we put a 3 in front of the CO2, we've got 6 more oxygens. So in order to get to that, what do we got to do? Well, we got 10 oxygens. How can we get there? They show you. and your math would tell you, you just put a 5 in front of the O2 and you have balanced this thing. Is there a set rule on what atom that you solve for first? No. It's just kind of learning to work with them and making sure at the end of the process that everything adds up. All right? And to try to do it with the least common multiple on the outside of the stoichiometric coefficients. So they didn't even define stoichiometry, did they? So we won't bother with that either. But so we have reached the end in terms of the introduction of something, as I've said, that you will be using for the whole course. So needless to say, this is really important stuff. It's really important for you to do your homework in terms of practicing, because that's all you're doing, learning to count numbers on one side, work the little bit of math and make them equal. All right? If you have questions about this stuff, I get it, because every year I got folks that mess this stuff up. I've got folks that miss this stuff all year long. I don't know what to tell you other than you got to practice, and if you don't understand, call me or email me and we'll go through it again. We're not done with balancing chemical equations. We will revisit this. We'll practice it together in the modules to come, but you just have to learn how to do this stuff. All right? Is there questions? Any at all? All righty.